Hi, my name is Thinh, student ID 229552225, and this is my student ID card. In this video, I will walk through my solution for programming assessment part 2. Part 2 is stands part 1, but instead of focusing only on correctness, the main concern here is efficiency. The input file is much larger, so the program needs to be fast. I will cover more four main sections: the work class, data structure I chose, additional code including sorting in helper functions, the build lexicon function, and finally the skip list implementation. The work class. So I'm keeping it exactly the same, since the core logic for representing a work hasn't changed. So the work class has three attributes: work stores, the spelling in lowercase, frequency counts how many times the word appear, and neighborhoods, the list of neighboring words, and the comparison methods that LD, LDLA, GTGEEQ are essential. They let Python compare two word objects directly using operators like less than or greater than. Without them, Mershot would raise a tire error when trying to compare objects during sorting. For the data structure, I'm using a Python dictionary. Just one line of code here. The key is the word string and the value is the word object. I chose this over a list because dictionary lookup is O1 on average compared to ON for a list scan. This makes a huge difference when reading a large input file with hundreds of thousands of tokens. And then we move on. Additional code. The sorting algorithm I chose is Mershot, which was told in which three of the subject. Mershot organizes all and log in all cases, best, average, and worst, which is significantly better than the purple source I used in part 1, which equates to all elsewhere on average and worst case. The merge function divides the list in half recursively until we reach single element arrays. Then the merge function compile to sort it half back together in order. For 10,000 unit words, Microsoft needs around 130,000 comparisons compared to roughly 100 million in PurpleSoft. For insertion sort function sort the neighbors list alphabetically. I show insertion sort here because neighbors lists are typically very small, usually fewer than 10 words. For small arrays, instruction sort outperform merge sort in practice due to lower constant factors and no recursive overhead. It was also covered in with two of the subject. And its neighbor function checks whether two words are neighbors, same length, different by exactly one letter. I use zip to compare character pairs, count differences with a variable called diff, and return early as soon as diff exists one to avoid unnecessary work. Let's run. So next we build the build lexicon. The read data function reads the input file and returns a dictionary. For each token, I strip non-alphabetic characters using its and convert to lowercase, and then check the dictionary. If the word already exists, I call add frequency to increment the count. If not, I create a new word object and add it to the dictionary. This gives O1 lookup per token instead of ON scan from part 1. And add neighbor function use a key optimization, like a comparing every work against every other work, which is OS where I first group words by length into a dictionary called group. Since two words can only be neighbors if they have the same length, I only compare words within the same group. This significantly reduce the number of comparisons, especially as the lexicon grows larger. The build lexicon, the main function has four steps. First, read all words into dictionary using rich data. Second, convert the dictionary values. to a list and sort it alphabetically using merge sort. And merge sort returns a new sorted list, so I can assign it back to the lexicon list. Thus, compute neighbors using as neighbor for write the sorted lexicon to the abort file. Let's run. And then you can see that dl.txt appear here. So I check. Yeah. And the solution secure execution time is it. Let's run it. Skip list is the second data structure I'm implementing for comparison. A skip list is a multi-layer linked list. It's not had multiple forward pointers. One per layer it occupies higher layers span more nodes, allowing the structure to skip large sections of the list during the search or insertion. So when searching or inserting a work, the algorithm starts at the topmost layer with the fewest nodes, move forward until it would overshoot the target, then drop down to the next layer and repeat. This is similar in concept to binary search, but on a link structure, giving a lock-in every time for both search and insert. And skip node store a work object and an array of forward pointers, one per level. Skip list maintains a header node, tracks the current hiding level, and use max level of 16 with probability p of 0.5, meaning it's not have a 50% chance of being promoted to the next level. The insert method places the work object in the correct solid position and updates on forward pointers at every level of the new node occupies because students maintain alphabetical order during insertion. No spirit sorting step. According to list, simply traverse the base layer to get all words in order, and the short method use the same top-down traverser to find a word by spelling, returning the word object or none if not found. Basically, skip list. This function reads the input file and inserts directly into the skip list. Searching first to check for duplicates while on tokens are processed. To list retrieve the already sorted lexicon. Add neighbor compute neighbors the same way as before and write data outputs the result. The key trigger compared to dictionary approach, dictionary lookup is O1 but requires a spirit O and log in sort at the end. The skip list you O log in but inserts but avoids the sort step entirely. In practice on the test data, the dictionary plus merge sort approach was slightly faster. Next, we run the skip list solution. And this is the is our skip list. And then we run skip list solution execution time. Yeah, you can see that. To summarize the key design decisions, I replaced the list with a dictionary for O1 work lookup. Switch from purple sort to merge sort for O and login. Sorting. Group works by work. Group works by lane to reduce neighbor computation and implemented a skip list as an alternative data structure for comparison. Thank you for watching.